Maximum entropy creating probability distributions may feel abstract. So let's start with a picture. You arrive at the beach one day in your car. Before you see the beach, you hear someone say, "The beach is very crowded today." What image comes to mind? Maybe something like this. Lots of people spread across the sand, but no particular spot stands out. Then you hear another person say, "A streamer is here." Now a different picture comes to mind. It is still crowded, but the crowd feels concentrated near the streamer, then gradually spread out around him. The number of people in these two pictures may be similar, but the information changed, so the mental picture changed. That is the whole idea of the maximum entropy we are going to translate into math. Let's build that intuition slowly. A probability distribution is shaped by the information we have. If all we know is the beach is crowded, then we know that there are many people, but there's no reason one location is preferred over another. So the most likely picture is just for people to spread out. Then if we add the information, there's a popular streamer. It will change the probability distribution. Now we expect people to gather around him. But here is the key. After using that information, we still do not have any information left, so we just let a crowd of people to spread out in the most natural, most random way. This is the intuition of maximum entropy. Information are treated as constraints. Once those constraints are satisfied, we choose the most random distribution. Mathematically, the objective is to find the probability distribution with maximum entropy that satisfies the information as constraints. That may still feel abstract, so let's look at two concrete examples. First, the uniform distribution can be generated with maximum entropy. It is the case with no explicit information. So none of the position is special. The left side, the right side, or the center will all have the same probability. But implicitly, P still needs to be a probability distribution, so the density must integrate to 1. For the second example, the Gaussian distribution can also be generated with maximum entropy. But the information is more specific. We need to know the expectation and the variance. So those become the constraints. The expected value of the distribution equals to mu, and the variance equals to sigma squared. After satisfying these constraints, we just choose the most random distribution. And this gives us an optimization problem. We want to maximize the entropy subject to the information constraints. In general, we can write this as find P star, the distribution that maximizes entropy. For a continuous distribution, entropy is written as negative integral P of x times log P of x dx. Then for the constraint, implicitly, we need the probability function to integrate to 1. And for the explicit information, we can set the integral of P of x times f of x equals to some constant. We can have as many constraints as we want to encode information. For the uniform and the Gaussian distribution, their constraints can both be written in this form. If you are only here for the idea, you can skip this derivation. But if you want to see where the exponential of the probability distributions come from, we can walk through the derivation together. For simplicity, this derivation is based on the discrete probability distribution with only one information constraint. The probability distribution can be represented as a vector or a histogram. Even though this derivation is simplified, for the more general continuous distribution with multiple constraints, it can still follow the same structure. To solve for the probability vector, we first write the Lagrangian by combining the entropy with the constraints. Then we can differentiate this Lagrangian with respect to pi and set that to 0. And after moving some terms around, we get log of pi equals to a constant plus lambda times fi. After taking the exponent, we have pi equals to a constant times e to the lambda fi. We can use a constant z to normalize the probability such that the total probability equals to 1. This is the solution when the probability is discrete. For the more general solution, when the probability is a continuous function, we have p of x equals to 1 over z times exponential of a weighted sum of information features. Importantly, the shape of the probability distribution comes from the information feature fk of x. It starts off as a constraint of the optimization problem. Then it shows up in the final solution to determine the shape of px. To see how probability distributions are generated in this way, now let's plug in some constraints. We can start with the general form of the solution. P of x equals to 1 over z times exponential of a weighted sum of features. Let's start with the case of no extra features. So the exponent contributes nothing. It just equals to e to the 0, which is 1. That means p of x equals to 1 over z. So this distribution has constant probability, which is a uniform distribution. It can be generated with maximum entropy without any explicit information. For the second example, let's consider the information to be the expectation and the variance of the distribution. It means that the relevant information features are x and x squared. When we plug those into the maximum entropy, we will have p of x equals to 1 over z times exponential of lambda 1x plus lambda 2x squared. The lambdas are the multipliers related to the expectation and the variance, so the constraint will be satisfied. And very importantly, we notice that the x and the x squared shows up in the exponential terms. And this is exactly why the distribution is Gaussian. The lambdas and z can be solved using the Lagrangian multiplier. When we plug in the exact solution for those, we get the exact Gaussian density that we are familiar with. So this is a nice way to think about Gaussian distribution. It is the most random distribution after we fix the expectation and the variance. With just this one mechanism, maximum entropy can generate a number of familiar distributions. The probability distributions are determined by the information constraints. If there's no extra information, maximum entropy gives a uniform distribution. If we only know the expectation as a non-negative quantity, we get an exponential distribution. If we know the expectation and the variance, we get a Gaussian distribution. If we know the expected energy, given by the energy function E of x, we get a Boltzmann distribution. But more generally, if all we know are some information, we get the exponential family distribution. So to sum up for this video, probability distribution can be generated using information. And constrained on the information we know, we want to pick the most random distribution possible. So just like the beach example in the beginning, we want the probability distribution to be as random as possible. And when we change the information, we change the probability distribution.